Oh! Now remember, when the system is a chemical reaction, the change in energy that occurs is a change in potential energy. This means that we can model enthalpy changes graphically as a change in potential energy. So if I look at the reaction that we did at the beginning of the video, which is the combustion of propanol, it releases 4,028 kilojoules of energy, which by extension means that the enthalpy change here, since it's on the product side, it's an exothermic reaction, and that it is negative 4,028 kilojoules. Now, graphically, we can actually help clarify why it's a negative that we place here. If the system is losing energy, that means that as the reactants turn into products, there is a loss of potential energy, and that goes to the surroundings. So if I'm writing this graphically, the reactants would start here, let's say as a flat line, and their energy is static until they react. So it would be something like this, plus O2, plus 9O2 more specifically. And then as soon as the reaction takes place, that plummets. And then now we have stagnant form of potential energy. That would be the products, right? And until those products change, well, once the compounds are made, that is the potential energy that is stagnant. So I would see a dip in potential energy, right? And we know that that dip would be the kilojoules released to surroundings. Now, the difference between the reactants and the products, that change in potential energy is equal to the enthalpy change. So when we say that the enthalpy change is negative 4,028, that is merely the difference between here and here. And the reason why it's negative is because it goes downwards. So that value, if I take the difference between the reactants and the products, that decline, that would be negative 4,028. Now for endothermic reactions, remember that there's going to be an increase in potential energy of the system because the system or the reaction itself will remove energy or absorb the energy of the surroundings, and that's what actually causes the surroundings to cool. So because we can expect an increase in potential energy, the graph can be expected to go upwards. And that's particularly why if we look at this endothermic reaction over here in fuchsia, where I got calcium carbonate decomposes with 178 kilojoules of energy to produce carbon dioxide and calcium oxide. If I were to write this as an isolated value, we would say that the delta H is equal to plus 178 kilojoules. And the reason why we write a plus is because, as we could see here, it increases. So the change between when the reactants here turn into products, it gains energy to do so. So it's plus 178 kilojoules. And so that space over here would represent the enthalpy change of plus 178 kilojoules. And so unlike the endothermic reactions, or sorry, I should say, unlike the exothermic reactions, the endothermic reaction graphs should always be going upwards.